Hey, so now we're going to be talking about electric dipole in a uniform external field. Okay? Using what we previously learned of electric dipole and seeing what would happen if a dipole was placed in an external electric field that already existed. Okay? In a uniform external field. What would happen? Can you take a guess? So a dipole, just going back through what we already know, is a pair of charges that has an equal and opposite charge, equal magnitude and opposite charge, okay? So here we can have a positive charge. We can go ahead and call this Q positive. We can go ahead and call this Q negative, okay? So now what we can go ahead and do is, well, guess what would happen? Any guesses, you guys? This dipole would experience what we call torque. Now, torque is a force in a rotational motion, okay? So a dipole would rotate with an electric field. Let's say that we have here the uniform electric field, okay? And we have a dipole within that field with the positive being right around here, okay? And the negative being right about here, okay? We're gonna go ahead and call these A and B, okay? Now, if the distance would be, for example, 3L, okay, then the force on A, we could be able to go ahead and calculate that, okay? So now let's go ahead and say that for the force A, all right, so the force A would be equal to the electric field, times the charge, okay? So that would be Q. And this would be going in the direction of positive to negative, okay? So we have positive on this side, and we have negative on this side. Okay, actually, I'm gonna write that in another color, just so that we can make that out a bit easier. We have positive on this side, and negative on this side, because remember, it always goes from positive to negative, okay? So being this the positive charge, that would go in the direction of the electric field. So that would go in the direction of the electric field, okay? So then it would go this way, okay? Now going on with force B, okay, this would also be the electric field times the charge, but being how it is negative, it would go in the opposite direction, okay? So it would go opposite to the electric field, okay? There we go. And yeah, so what this would do is basically create a rotational motion, okay, which is what we call torque. Okay. And that would basically make the dipole rotate. Okay. So let's go ahead and talk about an example just so that we can understand this maybe a little bit easier. Let's say you have your phone in your hand. Okay. Now it can be any phone, doesn't matter. I'm gonna draw plain old iPhone or an iPod. And let's say that you apply a force of equal magnitude. Okay. We're gonna apply one right over here, and we're gonna apply one right over here. Okay. You apply it at the same time, and since they're of equal magnitude, well, what would happen? You would have a center of axis right there, and the phone would rotate clockwise, correct? Well, this is basically what happens with the dipole, okay? Do remember though that net force So no force is being applied. Net force is equal to 0, but torque is what is being produced, okay? And this is basically what we calculate. Now, you might say, how exactly would we calculate torque? Torque is, I'm gonna go ahead and erase this. Okay, so torque, I'm gonna write that with a big T. Torque, is equal to force times displacement, okay? Put a big old square on that. Now for displacement, this is a perpendicular distance between the two dipoles, okay? And that is determined by the length of a triangle that we form here with A and B, the two charges, okay? Or Q positive and Q negative. So I'm gonna go ahead and make a triangle here. Oh, that's a bit too big. Okay, I'm gonna make a big old triangle over here. And I'm gonna write down this point as C, okay? So what we're talking about is this vertical line right here. This one right here. Okay, and so the displacement here now turns into AC, which is this distance right here. Okay, and that turns into the displacement, which is basically the magnitude of that line. Okay, so going a little bit back into the formula, EQ, which is basically the force of A and the force of B. Okay, so we can go ahead and replace F with EQ. All right, and AC, which is the magnitude of this line. Okay, and it's also considered the displacement. We can go ahead and replace that with, and I'll explain right away why. I'm sorry, 3L sine of theta. Okay, and why is that? Because we consider this our theta. Okay, and well, sine is opposite, which is this right here, over hypotenuse, which is this right here. Okay, so that's why we're able to use sine. That's why we're able to use the 3L, and that's why we have theta, okay? And that's basically just some basic trigonometric rules, okay? Now, the Q and the 3L, okay? These are the two components of the product of a dipole moment. So we can multiply those two, and we end up with P E sine of theta. Now, I hope you remember your previous lessons because that's specifically what this is talking about, okay? So, as you remember with the dipole moment, okay, P is basically the charge and the distance, okay? So that's exactly what we have here, and we just replace it within the formula that we previously had, okay? Now, with this, we can now write that the torque, let me go ahead and make just a bit of space over here. Torque is equal to the cross product of dipole moment and the electric field, okay? So we're gonna go ahead and write that down. There we go, okay? And yeah, so that's basically what we have at the moment. Okay, I'm gonna need you guys to edit this out, please. Okay, I'm jumping back in 3, 2, 1. Okay, so that's what we basically have, all right? Torque is equal to PE, which is a cross product, okay, of dipole moment and the electric field. And then we have sine of theta, okay? And that's basically how we're able to find exactly the torque of this. And that's pretty much it on this topic, okay? So once again, electric dipole in a uniform external field, okay? What we do with that is the dipole rotates, okay? And it creates torque, and we're able to calculate that torque exactly with this, okay? And that's it. Hope you guys liked it. Thank you.